So I'll try to talk about some recent stuff, and in some sense, the goal of my lecture will somehow use the excuse of some recent easy-to-state percolation results that we obtained with Jason and Scott. But in some sense, the results themselves, the important thing in some sense is that they're easy to state. But as such, they might not be that important. However, somehow the more general, I mean, the ones I will state are not, the core of my talk. What I want to explain is to convey the fact that deriving the result reflects that one understands something new about a model, and how some new combination of ideas and concepts show up in the proofs, and I'll try to make sense of that. So more specifically, in the first part of the talk, I will describe these type results, and I'll give a bit of background on conformal loop ensembles and things that are needed to state properly some of the results. And then in the second part of the talk, which will of course be very impressionistic because the time is limited, and each of the elements of each of the bricks that we're using could be the topic of several hours of explanation and definition if you want to make everything precise. So my goal will be just to give you some impressionistic idea of some of the tools that we use, in particular why Liouville quantum gravity shows up there and is useful. Maybe I'll try to give you a slight impression what these quantum disks are that are part of this Liouville quantum gravity story that you have maybe already heard of if you have listened to some of the talks earlier this week. And then maybe as a sort of teaser for those of you who are not so much into these two-dimensional probabilistic randomness issues, but are more familiar with stable processes, one-dimensional stable processes and their variations, such as stable growth fragmentation processes or fragmentation trees. One of the outcomes is somehow to explain that all these two-dimensional random structures that we are constructing are in some sense in a one-to-one correspondence to things that have to do with stable growth fragmentation trees. Okay, so let me start immediately, and so I'll start with the critical bond percolation on the square grid in the upper half plane. So maybe I can, just look at that. So you just look at the upper half plane. So we are looking at, this is the bottom half line here of the upper half plane that I try to show with my little pointer. And each edge of the lattice is open or closed with probability 1/2, right? We're looking at the critical bond percolation model. So each edge is open or closed independently with probability 1/2. And you have a picture like that if you have a portion of the lattice, but of course it's supposed to extend all the way up there. Now, that's the usual bond percolation model, and one is interested in these models in the clusters of percolation. Now we're going to do something different, which is having to do with these divide and color models or something like that. So we are going to, once we did this first step, which is sampling this percolation, where for each of the clusters that we see here, we're going to choose at random with a coin toss, probability P versus 1 minus P, to color them in blue or red. So you end up with a picture like that, where each, you sort of see the bottom cluster here was colored blue, this one was colored blue, and this one colored red, etc. And the coin with which we color these clusters in blue and red is not necessarily fair. It's it could be 1/3, 2/3, right? So there's a parameter P in the model, which is what is the probability that a given cluster is colored in blue in this picture. Okay, and now what we do is that we look at the blue cluster. So we sort of forget, we erase the initial percolation picture, and then we are left with just the coloring of the sides of the upper half plane. And now we looked at the connectivity properties in the sense that, you know, what are the paths that you can draw by, say, starting from the origin all the way to, by staying only on blue vertices. So the question I'm going to ask is, what is the size of the cluster containing the origin, of the blue cluster containing the origin for this model? And based on, you know, standard Russo-Seymour-Welch ideas from percolation, it's sort of easy to see, to guess that the probability that this cluster will be of diameter greater than r will decay probably like a power law, first order r to the minus a when r goes to infinity, right? The probability to make it far away will decay like a power law, and there's an exponent r which depends on the parameter p. Of course, you know, the more blue clusters there are, the easier it is to make it far away. Particularly if p is close to 1, you would expect this exponent to be very close to 0. Now, the question is, what is this exponent, right? So if you assume that critical percolation is conformally invariant in the scaling limit, which is something that everybody believes is true for the bond percolation on the square lattice, what is this exponent a? And here's the answer. If you assume that critical percolation is conformally invariant in the scaling limit, we have the explicit expression for this exponent. And of course, the formula itself, I mean, you know, there are different type of mathematicians and different type of motivations about why to do mathematics. It goes all down to our own personal history, maybe about what we are interested in, mathematics or not. I personally, I don't care about the explicit formulas. I like it when these explicit formulas reflect some deep understanding of an actual mathematical object, in that case, these percolation or percolation cluster models. And this is the fact here. There is one feature I want to say, that this dependence in P, which involves this arctangent function here, is very unusual in the context of two exponents for critical models in 2 dimensions. So it sort of suggests that something different is going on here, as opposed to the usual critical exponents that various people, including myself, have been deriving about 2-dimensional models before. So yes. One little comment I can make is that when P is very close to 0, and I'll come back to that later, when P is very close to 0, in some sense, the exponent, you know, the optimal strategy is to, it costs you very much, a lot to find a blue cluster. And so the optimal strategy is just to very close to have one very big blue cluster and then color it in blue. So the limit when P goes to 0 here should be, and it is, going to give you something that is going to be close to the exponent 1/3, which is the one appearing in critical percolation. All right, so here is a simulation. Like all the simulations, a few simulations I will show in this lecture, they are due to by Jason. So here what you see is somehow a picture not in the upper half plane, but in the very, very fine mesh, but in the disk. And what you see here is somehow the blue and red boundary touching clusters that you have here. So if you think a little bit about it, the previous question is related to the number, you know, if you look at all these macroscopic blue clusters in this picture, the big ones that touch the boundary, you know, how many, how many intersection points are there between these boundary touching blue cluster, very big blue clusters on the boundary, right? Because you want to, you take a point on the boundary, you ask the question, is it in a macroscopic, in a very big blue cluster here? That's the type of question we are looking at. Now, this previous result, which is a very, you can view it as a very, it's just a specific model, specific question. This previous result is part of a more general picture. And to start with, for those of you who know this story, you can replace this Bernoulli percolation and the Bernoulli clusters that we then color. You can replace these Bernoulli percolation clusters by so-called FK percolation clusters. And FK percolation, as probably most of you know, is sort of one particularly nice variation of Bernoulli percolation, where now the edges are open and closed, but not independently from each other. So it's a dependent percolation model. And the usual way you define it, one usual way to define it, I just write it down very quickly here, is that if you define the FK percolation model in a finite box, for a given configuration, you have a certain number of connected components defined by the open edges, and a number of faces that is defined by this configuration. And then you assign a weight to each configuration omega, which is proportional to square root of q, where q is a parameter in the FK model, to the power k of omega plus f of omega. So here, this is the critical FK model with parameter q in a finite box. And this, where q is equal 1, all configurations have the same probability, which means that you're just looking at critical Bernoulli percolation. And it is possible to extend the definition of such critical FK percolation model in the entire plane or in the upper half plane by letting the size of the box go into infinity. And then, then you have this percolation model. Edges are open and closed. You look at its clusters, then you color them independently in blue and red with probability p and 1 minus p, and you ask the same question. So now you have the first parameter, which is q, which is having to tell you something about how you chose the clusters, and now you have this parameter p, which is this coloring of the clusters. This model of coloring FK clusters is sometimes known as fuzzy Pops models or divide and color models, and has been looked at by various people, including Ole Hagström and others. It is an interesting model in itself, and I'll explain you in a moment also some other reasons to look into that. And here we get basically a similar expression for the exponent a that describe the decay of the probability. I mean, the decay exponent boundary, the decay of the boundary size. I mean, of the one arm exponent. Let's put it this way: boundary one arm exponent for this model. There's a general formula for A in terms of P and Q that I'm not going to write down, but I just wrote down here the formula in the very special case where Q is equal to 2, because that's the one for which it is actually known that the FK model has a conformal invariant scaling limit. This is the results of Stas Smirnov and his collaborators. And then you get, again, an explicit formula for the one arm exponent here. And because in that case it's known that the FK model has a conformal invariant scaling limit, this is not an unconditional result. This is a fact that this is a proof fact that now if you take an FK model with Q equal 2 critical in the upper half plane, then you color things with probability P1 minus P, then you get these. This is the value of the exponent that describes the decay rate of these one arm exponents. And it has a similar flavor, right? It is a sort of a feature here. When P equal 1/2, you notice that it takes a particular simple and nice value, because P over 1 minus P is 1. And then you sort of, this is closely related. This is just the one arm exponents of the Ising model. I'm going to comment to that in a moment. And again, when P tends to 0, it corresponds to the one arm exponent of the FK percolation model, which is also known where Q is equal to 2. All right, so let me just try to motivate also this, that it is a natural thing to try to color FK models, these FK percolation pictures. And one reason is that it is something very special happens when p equals to 1 over q. So in particular, when q is a positive integer, and then instead of coloring this in two colors, with probability p1 minus p, you have q colors at your disposal, and each cluster is colored independently in one of the available colors with probability 1 over q each. Then you get a coloring of your domain in q colors, right? Each site is assigned one of the q colors. And the obtained coloring is actually turns out to be the critical Potts model, which is very easy to define directly. So in particular, for this special value of p, when you start with an FK model, then you color independently the clusters, the obtained coloring has some nearest neighbor interaction feature, which happens to be the case only for the special value p equals 1 over q. Right, and that's if you color into q colors. And now if you color into two colors and with probability 1 over q, 1 minus 1 over q, then if you just look at the blue clusters, well, it's exactly the same law as one of the q colors in the previous case, right? So you put the previous case into two packs, blue and non-blue, and you get exactly probability 1 over q, 1 minus 1 over q. Okay, so we see that something special happens in the discrete case. And now I sort of start to recalling you a few things about what is believed about these FK model, percolation models in the large scale limit, because that's what we're interested in here when we let capital R go to infinity and look at these arm exponents. I remind you that when q is smaller or equal to 4, these FK percolation models are conjectured to have a continuous scaling limit with some conformal invariance properties. And now I'm going to go very fast, of course, and now maybe that gives me the occasion to say that a number of my heroes in probability have sadly departed and recently have passed away. And I always remember when I say the word scaling limit, I can hear Boris Cyrilson with a big smile saying that one has to be very, very, very careful about what one means when one takes a scaling limit. And so here in that case, what I mean under scaling limit, what one means is that the collection of macroscopic clusters, when you take a fine mesh limit, would converge to something which you could describe either as a collection of clusters in the continuum, or that you could describe by the loops that form the outer and inner boundaries of these clusters. So Oded Schramm told us that if this limit exists and is conform invariant, as it's believed to be true, the interfaces will be one of his Schramm-Loewner evolution curves. That's for single interfaces. When you look at the entire clusters and the joint limit of all these clusters, then this will be described by the natural variation of the SLE model, which has to do with the SLE branching tree, as explained in a paper by Sheffield, and the corresponding conformal loop ensembles, which are just the collection of loops that you can define using these exploration trees, would correspond to the scaling limit of the joint collection of all the macroscopic cluster boundaries in the FK model. So this is proved for the square lattice in only for two cases, which is the FK Ising model, q equal 2, and the q equals 0 plus limit. Now I want to emphasize one thing, which is that the relation between, if I give you an FK percolation model q, I take the critical value and you ask what is the value of which SLE is going to describe its scaling limit, or which conformal loop ensemble is going to describe its scaling limit, then the relation between q and kappa prime is not something which is rigorously established. There are various non-rigorous considerations, mostly originating from physics, that suggest that the relation is q to kappa prime, 4 times cos square 4 pi over kappa prime. And you see that here we start getting some of these trigonometric functions here back into the game. So in particular, you see that Q will vary between 0 and 4, which is what is it's known now, thanks to efforts of recent efforts of a number of people, that Q equal 4 is indeed the threshold for the critical FK model to be exhibit a first order phase transition. Anyway, so this is how the picture looks like in the large scale limit. If you try to draw in different shades of gray the different clusters of FK percolation that you see, and maybe you map them on the disk because it's easier to picture, you get a collection like that. So then you first have a picture like that, and then it is natural to say, well, given what I said before, to say, well, we can try to color independently in blue and red all these FK clusters with probability P1 minus P, and then look at the blue and red clusters that one obtains. So this is the natural thing to do. And in a first paper a couple of years ago with Jason and Scott, we showed that for each of these CLE kappa prime models, there exists one special value capital Q, such that this coloring of CLE kappa prime loops with probability 1 over Q and 1 minus 1 over Q, for one of these values, something very special happens, namely that it has a feature that can be interpreted as reflecting nearest neighbor interaction model. So that means the obtained coloring is just a nearest neighbor interaction, meaning it is the same property that the one reminiscent of the Potts model that I described before for Q. So in particular, this shows that the only possible conformal invariant limit of FK loops is the CLE kappa prime for this particular value of Q, when Q is equal to capital Q of kappa prime. However, in this 2017 paper, we did not establish the general formula for Q over kappa prime. We just said, well, there is one. Now, in this recent preprint, we showed that the value is actually the one anticipated in the physics literature, namely capital Q is this 4 cos square of 4 pi over kappa prime. Right, so we see that out of just conformal loop ensemble configuration, which are these continuous families of loops that are defined in the model, you get, for instance, the fact that when kappa prime is 24 over 5, say, then this corresponds to some sort of notion of conformal invariant colorings with 3 colors in nearest neighbor interaction. So that would be the one supposedly related to the Potts models with 3 states. Okay, so I hope I gave you a little bit of motivation, right? So it depends on your taste. Either maybe you're just interested in saying, how on earth can one get these strange formulas for A of P, or where do these type of things come from? How do you derive this capital Q of kappa prime, equal 4 cos squared, etc. What sort of conceptual ideas come into the game when one tries to derive this model? Now, I need to be slightly careful because I need to make sure I'm not running out of. Be careful with time. Okay, I'm running out of time very quickly, so I have to speed up. So the second part of the talk will be trying to explain you some of the underlying ideas. So the first remark I want to make is that in both cases, the goal somehow is to look at this picture where you color, you start with a CLE kappa prime, which is a continuous model of collection of loops. Then you color them, and then you look at the interfaces between blue and red, which is these green curves that you get there. Now, in both cases, it is all about describing the law of this green interface. And once we've described this law, we can look at how much it intersects the boundary. That was going to tell us the exponents A, and some other features of its law will tell us the locality type property, the nearest neighbor type property of this blue-red coloring that I explained before. So in some sense, the goal of the game is start a CAD kappa prime, color it in blue and red with independent coin tosses P1 minus P, and just try to describe what these green interfaces are. All right, so let me immediately jump to the little movie. So this is something I'm going to show it several times. What I'm going to show you now is the following picture. I'm going to look at just the interface between, in a square, between the set of red clusters that hit one side, one half of the square, with the set of blue clusters that intersect the other half of the square. So let me just show you that very closely. And we're exploring this green interface slowly, progressively, so that you see how things happen. I let it run through once. Right, so here what happens, whoops, I should have, right, so what we're doing here, let me stop here. What we're doing here is we're exploring the interface between the blue, so blue is, you have blue with probability 2/3, red with probability 1/3, so you will have more blue than red. And this picture is for percolation. So we started with a critical percolation model, then we color the clusters of percolation. And then we look at the collection of blue clusters touching this half. It will have an outer boundary, which is this green, the cluster of blue clusters touching this half. We'll have an outer boundary, which is this green curve, which happens to be the same by some sort of duality feature that than the lower boundary of the set of red clusters that touch the other half of the boundary. Now, in this movie, what you see is that we are exploring this interface, and as soon as the interface hits one of the blue percolation clusters, it discovers the entire percolation cluster. It's right. So here, what you see is that you have this. So there are different shades of blue and different shades of red. They are just there so that we can differentiate between the different blue clusters, the different blue percolation clusters that then put together are forming this giant blue cluster of clusters. Now, what you see here is that when we arrived here, we discovered this blue one is there. And when we arrived somewhere here, we discovered this fairly big red one here. So we know already that the green curve will have to go, makes its way through these green-blue pockets, right? The reason why it is natural to try to look at this procedure when you sort of discover all these percolation clusters at once is that if you look at the conditional law of the remaining to be discovered picture conditionally on what we have discovered so far, well, in that case, it's pretty clear that here we're going to have independent percolation clusters that are going to be colored independently in blue and red, independently of everything that what has happened before. So in particular, we sort of see that there is some sort of nice Markov property that comes into the game when we sort of decide to discover all the percolation cluster as soon as the interfaces hits it. So if we go, say here a bit further back, right? So here at that point, we have discovered all this, and we know that we'll have to go, through all these various pockets that are, squeezed between these blue and red clusters we have already discovered. And then when we are out here, we're in open territory, we'll discover, percolation clusters that are in this area here. So let me just go the movie slowly again. All right. So this sort of shows that it's sort of for those of you who remember the conformal Markov property of SLE, which is the one that is behind the scene. It is what we get here is that the natural process that one is looking at here when you do that is actually, the discovery of a percolation cluster of one of these red or blue clusters happens at once, right? So in some sense, the discovery of a percolation clusters can be viewed as some sort of a, Poissonian event, and we can sort of view the red cluster as, appearance of one of these clusters as a jump in jump process, right? And indeed, that's sort of one of the things that we did in the CLE percolation paper. If you use this idea that the stationary picture that one explores, this idea of sort of renewal of the picture after each of the jumps that correspond to the discovery of these loops, plus the fact that the loops, the law of these loops being that you discover, right, of these jumps, CLE kappa prime loops is known because it's CLE kappa prime, which is something that is well understood. This sort of gives you a description, quite a lot of information already about these green and interfaces and these blue and green objects. And in particular, is that what you get is a description of the green interface, but you are missing actually one parameter. So this tells you what the candidates are for the law of the green interface. It's a one parameter family of green laws on possible green curves, but the relation between which of these green curves corresponds to which of these values of P is actually not coming out of this approach. So we are still we are still missing one ingredient, which is exactly the status after our paper on CLE percolation for a couple of years ago. So the new trick is new input is to use additional and independent Liouville quantum gravity and additional independent Liouville quantum gravity structure on top of this entire picture of these colored CLEs that I've described here. So, so before going into that, for those of you who don't not so knowledgeable about Liouville quantum gravity, I just want to make a few general browse very quickly to mention the fact that there are an amazing number of very nice developments on Liouville quantum gravity and have been taking place in these last years, but they go on at least 4 or 5 different fronts, so they can mean very different things. So here I listed 4 bullet points where different approaches or to Liouville quantum gravity, which is all related to trying to define fluctuations away from the Euclidean area or the Euclidean metric in the plane. So what is the random metric or random area measures that you can define in the plane that are natural from a physical perspective? And you can mention the approach by random planar maps. So this is sort of a discrete model, and I mentioned quite a number of those names that were involved in these things, lots of French people there. You have the continuous approach by mating of tree and SLE processes and conformal weldings that has been initiated by Scott Sheffield, and then you had all these very important development with Duplantier and Miller, and then further work by people like Ewen Gwyn, Lina Holden, or Shin Sun. And then you have another, very recent nice work which has to do with how to define the random metric out of, the GFF and out of basically the second approach. So these are recent sequence of papers by Gwyn, Miller, and Ding, Jan Ding, with Dunlap, or partially with Dunlap, Duvida, and Falconet. So there are very important things going on there. And then, of course, there's also the sort of continuum approach via somehow explicit Gaussian free field integrals construction and computations. So these are, papers by Rode, Vargas, Kupmachainen, François David, and Guillaume Remy and others. So all these things have to do with more or less, the same things, and some of the challenges, of course, have to do with the fact to relate each of these items with each other. But there are somehow quite different approaches to this. So here, what we're doing is we're taking the approach of the second bullet point, which has to do with these mating of trees and the sort of geometric approach by SLE process and then weldings. And we relate it to some features appearing in the first one, which is the discrete settings, and in particular with the sort of called peeling algorithms. That is sort of one of the main tools used to study those. And you can look at Nicolas Curien's webpage with this some floor lecture notes, which is basically devoted to the discrete aspects of the peeling algorithms. So very quickly, some general ideas. I just do that to see that I'm doing bad with time. Some general ideas of the proof. So the first one is what is Liouville quantum gravity that we're going to have in mind is that there is a parameter gamma that is closely related to our parameter kappa prime, such that it is possible to define some sort of a natural random function in the plane, non-negative function in the plane that you can interpret as the exponential of gamma times the Gaussian free field. The construction of these very rough generalized function goes back to people like Herb Krohn and Jean-Pierre Kahn, which then you can use as a density measure with respect to density, with respect to morally density with respect to Lebesgue measure, even though this is of course not a regular density because the function is a generalized function, but you are able in some sense to define in the domain D a random area measure that sort of to each portion of D assigns a random area. And this is rather rough, meaning that the support of this area measure is not smooth, but it's dense in the domain. Furthermore, when the boundary conditions of H are chosen well, having to do with so-called free boundary conditions, you can also make sense of a boundary length measure on the boundary of the domain induced by this random area measure. So meaning that you start with the Gaussian free field and you're able, in the domain, you're able to define, assign to each portion of the domain a random area, and to each, arc on the boundary, you are able to assign its boundary length, which is random. Now, a simply connected quantum surface in the way devised by Scott is essentially now an equivalence class of triplets given by a domain and an area measure and the corresponding boundary length measures. But this is an equivalence class under conformal transformations. So meaning that if I distort my domain D by conformal transformation, well, you have the push forward of the measures mu and nu that are defined in this way. In some sense, when I give you an equivalence class D mu nu, it doesn't tell you what D is, because by Riemann's mapping theorem, you can always map a simply connected domain onto each other by conformal transformation. It just tells you somehow that if, how mass area is sort of distributed within the domain D, but you don't know the shape D because you are working with equivalence classes. So in some sense, what you have is a little bit like a Play-Doh, an area of Play-Doh on which there's an area measure. But the area of Play-Doh, the Play-Doh can always be stretched conformally using Riemann's mapping theorem, and you don't know which version of this Play-Doh thing which stretching of this particular area measure you are playing with, because you only see the object. Now, the important initial observation by Scott was that when you draw an independent SLE kappa type curve on top inside a domain D equipped with one of these measures, area measures, then it is possible to make sense of the quantum length so of some length of this curve, this SLE curve that is drawn in this domain D. You know, for a normal curve, typical curve in the domain, you can't make sense of the length defined by mu, but in the case of SLE curves, for one value of kappa and one value of kappa prime associated to the gamma you chose with to start with, you can make sense of what the length of this random length of this curve is when you draw it on an independent SLE curve on top of one of these quantum gravity quantum surface. So in particular, if I superimpose, I take a domain D equipped with a area measure mu, and I draw on top of it an independent CLE kappa prime, then each of these CLE kappa prime loops gets a length. Right. So now, in particular, if you now look at the interior of the CLE kappa prime loop that you have drawn on top of this quantum surface, its interior is now going to be made of connected components, and each of these connected components will correspond to one of these quantum surfaces, which has a finite boundary. Okay, so I have to rush. So here, let me just explain you, draw you, take my little pen and just try to draw you what I have in mind here. So we have a domain D here. And inside the domain D, you sample a CLE kappa prime. So here I'm going to draw one of these CLE kappa prime loops in here. Right? This is a loop which has double points, but not self-cross, no self-crossing. So the interior of the loop will be, everything that is sort of here. Right here. Each of the connected components of the interior of the loops is a simply connected domain. And inside of this thing, which has a finite boundary length, and each inside of this thing, you get a quantum, therefore a quantum surface, because you have a domain equipped with the trace of the area measure that you started with inside this domain. Now, the feature, which is sort of the crucial feature of, and I really need to speed up, I guess, yeah. So the crucial feature in this whole business is the following. Suppose that you draw, let me go back to the movie here. Or let's draw this picture here. Yes, do this. Suppose that we have drawn that here in this square, there is a random area measure. And suppose now that we do this discovery process. Now, the feature is the following, that each time you discover a loop, an SLE loop here, a CLE kappa prime loop, the quantum surfaces that are encircled by these loops, right? They appear one after the other, and you're looking for each of these loops as, you take the outer perimeter and you look at the quantum surface that is inscribed by it. A priori, you would guess, of course, that, H has correlation, what happens to the quantum area here and what happens to the quantum area there. It's very, it's very much correlated, because there's a correlation between what the Gaussian free field is doing here and what it's doing there. But what happens is that along the way, when you discover the green curve, the magic feature is that the collection of quantum surfaces that correspond to the interior of each of these successively discovered CLE kappa prime loops, they correspond to a Poisson point process of certain quantum surfaces that are called quantum disks. So in some sense, one way to understand this is to say, well, a quantum disk is in some sense what is typically represents what happens inside a CLE kappa prime loop drawn on, in an ambient CLE kappa prime object, in an ambient LQG surface. And in this discovery procedure, when you do have, when you discover, these loops one after the other and look at their interior, you get exactly a Poisson point process of quantum disks in front of you. So in particular, one feature is that you start exploring a quantum disk, that means the interior of a CLE kappa prime loop, and then you explore inside there, well, you get the similar stationarity feature, meaning that all the remaining to be discovered domain that you have to continue to discover, there are going to be discoveries of Poisson point process of quantum disks. And therefore, the law of what remains to be explored is still a quantum disk itself. So I'm going, very, very, very quickly. I jumped a number of features, but the main message is that when you equip the CLE kappa prime by LQG random area measure, and when what you discover, what keep in mind when you discover these various things is not the shape of the loops that you're discovering. You just discover the inside, what is inside used as a quantum surface, right, as an equivalence class. If this is the information you collect, then you have a really nice, stationary Poisson point process discovery feature that you get there. So this is the continuous analog of some features that appear in the discrete case or in random planar maps, which is exactly, the magic and the nice features of this peeling algorithm. So this is the first result that I mentioned. The point processes of quantum surfaces that you discover correspond to a Poisson point process of certain quantum surfaces called the quantum disks. There's an additional feature, which is the more difficult one, which is to say that the surfaces that are cut out, that you leave aside when the green interface hits a boundary, they also form a Poisson point process of quantum disks. And all these features are reminiscent of results that appeared in the mating of tree paper by Duplantier, Miller, and Sheffield. And indeed, they are derived. These are some of the CLE version of those results. So it's building on this mating of tree. So as a consequence, you get that if you, instead of going from the bottom left corner to the top left, the green interface is used to define some sort of a branching tree, what you get is a variant that we can describe very explicitly, variant of this stable growth fragmentation process that can be analyzed using the tool developed for some processes, because each of the boundary length of the CLE loops that you're discovering will have some scaling variance properties. So the corresponding jumps corresponding to the appearance or disappearance of loops will correspond exactly to the jumps in a stable growth fragmentation process. Okay, I'll jump that. I just want to mention here that at one of the end results is saying that if I start from a stable growth fragmentation tree, it enables you to reconstruct the couple CLE loops LQG surface of these two independent inputs together. So in some sense, what you get is that there's a natural bijection, reminiscent, of course, of the bijections that appear in the discrete planar maps, but here it all takes place in the continuum and uses completely different ideas to be derived of the couple CLE independent LQG surface. If you put them together, this is sort of isomorphic to defining a stable growth fragmentation tree. Of course, I did cut a number of corners in the statement I just made. You can look at the paper if you want to have the precise statement. Let me very briefly mention where the formulas come from at this point. So the way the formula for A of P and also for the cosinus square comes from goes as follows. It's a basic fundamental formula, and then when I see this, I always remember the nice people working on these things while I was back when I was a student, Rondoni, and people like that, and of course Jean Bertois, from whom I learned all these things. That if you take a asymmetric stable process of, say, alpha smaller than 1, so that's, say, for instance, your difference between two independent stable subordinators, and you have one parameter, which is the ratio between the positive and negative jumps. So it's a stable subordinator minus u times stable subordinator, or the other way around. Then if you look at this running maximum, this will be also, if you look at the jumps of the running maximum with time, this will be also a stable subordinator, right? Its jumps will correspond. And there's a nice formula that relates the index of this new subordinator with, in terms of this alpha and this u. And of course, our organizing of one world probability seminars, Leif and Andreas are, of course, very much into these type of things. So equivalently, if you know alpha and beta, you can recover what the asymmetry parameter is, u. And this is the type of formula and inputs that you are using in the framework of these stable growth fragmentation trees that you relate to the discovery of these models, that where, this is the origin of these arctangent, say, in the A of P formulas that I started with. So somehow these type of relations having to do with how to relate an asymmetric stable, the asymmetry parameter u will be related to P in some sense, because it will tell you something about left-right asymmetry. I'm cutting lots of corners. And somehow we know alpha and beta by some other consideration. Sort of that enables you to relate, the value of P to the value of alpha beta, which are related to the identification of the green interface among the one parameter family of possible candidates. Okay, so here I was trying to explain you a little bit this story about why, if you discover the percolation clusters that are touching the boundary one after the other from the left, where these how to find this stable subordinator and difference between two stable subordinators and the range of the maximum geometrically, but I don't have time to do that. Okay. So I think that's concludes this talk. I hope I wasn't, maybe, obviously I'm not able to give you insight of all the definitions of LQG in the limited time, but I hope that for some of you, I tried to give you some motivation and gave you, some wish to try to know more about what these quantum surfaces are and how to glue them. And as a reference, so here the papers that I talked about, the results about that I discussed is in that preprint. The previous yearly percolation papers that it builds on, is in this one, and two very, very closely related paper. Everything is with Jason and Scott. The series are here, those ones. In particular, there's a very nice story having to do with what happens when you color conformal loop ensembles for those loop ensembles that are not boundary touching and not touching itself. And so there's something intriguing going on, which has to do with the fact that the stable the asymmetric stable processes that happen, that appear there are, corresponding to an alpha between 1 and 2. So these are sort of a slightly more complicated asymmetric stable fragmentation trees, if you want that to appear there. Okay, thank you very much. I thank you for your attention, and I apologize for maybe not being very proficient in using my laptop in front of me in this little room here in
Thank you, Wendelin.
Place where it's raining now. Okay, thank you.
Thank you. Let's thank Wendelin. Since the next session will start very soon, if you have questions, please send to the chat or send to Wendelin directly. And there is an announcement from Sibar, right? Sibar, where are you?
Yeah, no, yeah, I'm here. You can ask a quick question. Perhaps we have another room meeting happening soon after this.
Oh, okay. So, is there any question? Oh, yes. Do you, Andreas? Oh, what's happening?
There is one on the chat asking what about bulk exponents from Christoph Gerber.
Ah, okay.
What about? I'm sorry, I didn't hear.
What about the bulk exponents?
Yeah, well, I mean, it's of course a natural question. I mean, for all these, one has to be careful here because it's a slightly different story. The moral is that there are quite a number of other exponents one can derive here, but not all. Let's put it like this. And the bulk behavior. So, for instance, it's if you look at what I just said, these interfaces when they're in the middle, these green-blue interfaces, there will be SLE type curves. So because you are inside the domain, the influence of this P1 minus P will not be felt that much when you are inside. So it's a good question. The answer would be quite longish, but morally, indeed, you can derive not. I focused on this particular one, and that's what we did also in our paper with Scott and Jason. But again, that was more of a this was not our initial motivation. Our initial motivation was to identify the exact law of this green interface. And then once you have that, indeed, using consideration having to do with boundary conformal loop ensembles, gluing, and all sorts of things, quantum gravity ideas, actually, it is possible to derive a number of other exponents, including the bulk.
Thank you. I have some question which is not directly related to what you're talking about, but you have CLE carpet and others. And is there any work for constructing a process on that?
Yes, I mean, that's the other paper that you can, I mean, in some sense, the whole, okay, so you have two types of CLEs, the one that are boundary touching and the ones that are, where the loops are self-touching, and the one where the loops are simple curves. So this is the simple CLEs where somehow you have something which is like a, if you remove the holes, it corresponds like a Sierpinski carpet. And this SLE, this one that I discussed here, is the one when you remove the hole, it looks a lot more like Sierpinski gasket, touching points. So indeed, if you look at this paper here, this deals exactly with simple conformal loop ensembles in there. So what we are defining in this cycle of papers, so if you look at this one, simple CLE percolation, simple conformal loop ensembles, there is in some sense the whole structure of what would be critical percolation within the CLE carpet, right? So the law of the green curve is exactly describing what would be critical percolation living in the fractal domain defined as a CLE carpet. And the identification somehow of all these possible interfaces that you get there. Now, if you look at the QLE paper, so it's another three-letter acronym of Scott and Jason, it's sort of part of the things that we have in our drawer in terms of projects, which is that you eventually one can construct some natural harmonic functions, on the notion of harmonic functions in these carpets, and therefore make sense of some sort of a Brownian motion in the carpet. I know that's probably where you're trying to go to. But in some sense, it's a natural thing to do here. But in my personal take is that in this context, the really natural object to define in these CLE carpets is actually the percolation object. It's natural as a it's a natural exercise to say, okay, I want to have a random fractal. The CLEs are natural random fractal, and then we want to have diffusion there. But the way these CLEs are defined somehow makes them much more naturally corresponding to CLE growth mechanisms that have to do with these quantum these random distances and things like that that are related somehow to these invasion percolation inside the CLE carpets that you have there. So one thing we did, just a final thing, that in that paper what we construct, for instance, is the natural measure, the natural quantum measure that is going to live on the carpet and on the gasket when you equip it by the natural independent LQG object. So you have the LQG, you look at the trace of the LQG on area measure on this fractal, then you can make sense of the natural measure living, quantum measure living in the fractal. And as it turns out, it's exactly, it's just a natural limiting measure of the growth fragmentation tree, if appropriately looked at. That is the one that has been looked at by all these people working on these growth fragmentation trees. So it's the boundary measure on the growth fragmentation tree that you had before. But that's, one natural object. And what I want to say is that this natural measure is not necessarily the natural equilibrium measure of the, of the stationary measure of the Brownian motion. The Brownian motion will live in some other special places than the percolation lives in. So, these type of things.
Thank you very much. Thank you. So I think it's already time is over.
Takashi,
yes.
sorry,